Okay, so this is a quick video about polarity because that's one of the new things we just learned the past 2 days, and we have a quiz tomorrow. Um, well, this is my first time doing this kind of stuff, so bear with me, but I'll try to get through it. Molecular polarity. It's like 11 o'clock almost, and I'm like tired, so I might pronounce things wrong. Bear with me with that too. Everything I'm going to talk about is I researched online, so like it's 99% correct. Don't but it's like I'm just trying to help. I cannot guarantee all of it is all right, but I'm pretty sure most of it is. So this all thing is from one of the links I sent in the group chat, so you should be able to do it. I'll be just going through it and just explaining how I understand this, and might help you tomorrow's quiz. Okay, so a molecular polarity. Um, you to find if a molecule is polar or nonpolar, you have to find the polarity of its bonds. So there can be a molecule that has all polar bonds, but the molecule is nonpolar, and we'll talk about this later on. And you can have and obviously you can have a molecule that has no polar bonds, or like all nonpolar bonds, and therefore it's nonpolar. You can have a molecule that has polar and nonpolar bonds, and most common nonpolar bonds are hydrogen with anything with this bonded with any other element except nitrogen, fluorine, and oxygen. We'll talk about those. So like those are not, for example, are nonpolar bonds like hydrogen and carbon. Those are more common actually. Um, that is a nonpolar bond, which can have another element or atom bonded to it that is a polar bond, and that can be polar because it's asymmetric. We'll talk about that. And molecules that have lone pairs usually creates an asymmetrical distribution of bonds, which causes it to be polar. But not always. This is what I thought, that if you have lone pairs, it's always polar. Not true. We will talk about that too. We'll do some practice problems. It's also online. You can probably find them. So yeah, let's get to it. General steps. So when you start to determine if a molecule is polar or nonpolar, these are some general steps you can follow. It's also I got online, so yeah, I'll probably say that a lot of times. But yeah, none of this is mine. It's from a prep. It's like a prep thing for chemistry online by Mark Bishop. So credits to him. But this helps us for tomorrow's quiz. So first step is you draw a little structure, basic, so you understand. It's more or less to help you to examine the electron domains, which is like the third step, but it kind of gives you the overview. So once you draw the little structure, then you identify the bonds as polar or nonpolar. And this is what we did in our third packet. So this is in our third packet. It's best if you remember this. Not sure if we're going to get this. We will get the electronegative table, so this one with all the electronegativity. This is what I found online. So we'll be given this, so you will use this to identify if a bond is polar or nonpolar. So if it's between 0 and 0.4, the electronegative difference, it's nonpolar bond. If it's between 0.41 to 2.0, it's a polar bond, and if it's more than 2.0, it's ionic. For our purposes, or what I think it is, we don't really have to worry about this when determining if a molecule is polar or nonpolar. So you can forget about this. This is all we need to know, right here. Um, we okay. Further on, I'm not sure this is gonna be on tomorrow's quiz, but if the overall polarity of a molecule is nonpolar, it's going to be, we'll talk about that actually, never mind. Sorry for going ahead, I guess. But yeah, we'll talk about that in the next slide. So you find the polarity of the bonds. Then you examine the electron domains, and this is where you come into the lone pairs. So if there are no lone pairs on the central atom, and all the bonds, regardless if they're polar or nonpolar, are the same, then take a guess. Yes, it's going to be nonpolar because they're symmetrical. It's a symmetrical distribution of distribution of the polarity bonds. So let's do an example right here. I have like a small example right here. Some CO2. Let's see. I almost forgot. Okay, yeah. I already know this. You will have to like figure this out when doing the quiz. The structures. You can do the We know this. This is what we did in the first packet. The steps to doing the Lewis dot structure. You count the number of Felix electrons. Okay, let's just do the whole thing. So there is carbon has 4, oxygen has 6. So one carbon is 4 electrons, two oxygen, so 6 times 2 is 12, plus 4 is 16. You have 16 electrons. Then you do a skeleton. You actually only do one each. Then you give each of the terminal atoms a number of electrons until it fills up, and then you look at the middle one. So in this case, you need double bonds for it to work. I already know this. You can do it. It's not that hard. You'll be able to do it. Believe in yourself. Trust me. I didn't know how to do this anyway in the beginning. So this is the Lewis dot structure. Then you have to find out the polarity of each bond, because both bonds are the same. If you find one, you'll find both. Oxygen has how much? We can check right here. Oxygen has 3.44, and carbon has 2.55. So we subtract 3.44 minus 2.55, which is 0.89. And because oxygen is more electronegative, the direction of your polarity bond is going to be outwards from carbon. So it's going to be like this. And it's an electronegative difference of 0.89. And same here. So this bond right here is polar. It's a polar bond. And so is this, because it's greater than 0.4. However, because both bonds is exactly the same electronegative difference, and they're polar, and they are going in opposite direction, it cancels each other's out, and thus this whole molecule as a whole is nonpolar. And we'll go more in depth in the next couple of steps. This is because another factor that affects the polarity in a way is the shape or the geometry, the actual molecular geometry of the thing. And in this case, this is actually linear, and that's why it's non-polar. Okay, back here. If you have a molecule that has one or more polar bonds in the central atom, and if the other bonds are not the same, then it's polar. I mean, what else can it be? And these also are affected by the shape of the geometry, which is the fourth step. You have to determine the shape of the geometry, because if you this is kind of a shortcut right here. This is like a shortcut. If you know that there are no lone pairs and all the bonds, regardless, you need to know this, regardless if it's polar or nonpolar. If there are no lone pairs and all the bonds are the same, exact same electronegative difference, it's going to be nonpolar. But if you have one or more polar bonds on the central atom, and if the other bonds are not the same, then it's going to be polar. And to determine it, it's okay. To be fair, it's not always going to be polar. This is like a maybe. Most likely, but not always. And this is what I said in the beginning. Not if you have a lone pair, it doesn't mean necessarily that it's going to be polar. And we will come to that. So that's why you have to determine the shape. And so let's do an example for right here. This is a very common one, H2O. I remember learning it in ninth grade, and it's like really important because water has a really good has a very unique property, and that's because of its VSEPR theory, VSEPR shape, and molecular geometry. Okay, so H2O. this is very basic. I know this from before, so I'm just gonna quickly draw it. That was a fail. H2O has two lone pairs, and therefore it's bent. I drew it purposely like this, so I don't have to draw it again. This is also the shape, more or less. It is bent. I believe we'll be given, we know this, that we'll be given that Vesper and shapes of molecules chart paper, the chart with all the shapes and the bonds tomorrow. So this has a bond angle of 104.5. We don't need to know that, but I'm just saying. This is bent, and that's because of the lone pairs. But you will see cases where you will have two lone pairs, but it's not bent. Yes, yes, it sounds weird. I have a final example, which we'll talk about that. But yeah, you might have cases. So you have to look at you have to, if you know that you have one polar bond or you have lone pairs, you need to determine the shape just to be sure. So in this case, you have two lone pairs and you have a bent structure. The bond, I believe, the polarity bond. So oxygen is 3.44. We just looked at it. Yeah, 3.44, and hydrogen. You can memorize this. Hydrogen is common. It's 2.20. It's not that hard to remember. Just 2.20 right here. So I already know that. So 3.44 minus 2.20 is 1. I mean, yeah, 1.24. So you have a 1.24 going inwards. So we have this. So see, in this case, like now you might ask, or you might ask yourself, well, both bonds are the same. Why is it not nonpolar? Well, this is why, because there are two lone pairs which cause the structure to be bent. If the two lone pairs did not cause the structure to be bent and it still stayed linear, then it would be nonpolar, because it's not, because if it's linear, then it's stating more or less, it's stating that the electron pairs are canceling each other out. It's kind of weird, I know. This is how I understand it, but if the lone pair is affecting the structure, or if it's making it bent, and examples bent in this case is this one, a bent as in the tetrahedral category, or the T-shaped in the trigonal bipyramidal category, or the T-shaped in octahedral category. So like I'm reading this off the chart, um, but just I'm getting ahead of myself. But for example, the linear and the trigonal pyramidal bipyramidal category, sorry, is where there's three lone pairs and two connected atoms to the central atom, but it's linear. So in that case, the three lone pairs cancel each other out, and thus, if and only if the other two bonds are exactly the same, um, they will uh, they will be nonpolar, and I believe I have an example for that. So we'll come back to that. Come back to it. So yeah, in this case, it is polar because what we went through the first few steps. So the first step was, sorry, lost track. First step, we drew the Lewis structure. We identified the bonds. They are polar bonds, but because after examining the electron domains, uh, we have two lone pairs that affect the shape of the geometry, making it bent. Thus, because it's bent, this is where I forgot to talk about. Because it's bent, it's not symmetrical or asymmetrical. It's asymmetrical. There's an asymmetrical distribution of the polarity bonds. Symmetrical, yeah. And therefore, it is nonpolar. I mean, what am I talking about? It's polar. Now, to identify what kind of IMF it is, that's our next slide. I'm gonna skip this. These are pretty basic ones. It's in the packet. This is carbon tetrafluoride. This is just 1, 2, 3, 4. You have chlorides, and they're all the same bonds. I believe they are polar bonds, and because they're all the same bonds, there are no lone pairs. So no lone pairs, um, all the same bonds, that means that's the first shortcut, more or less. This one right here, the first shortcut, it's going to be nonpolar. So it's nonpolar. This one is the other example in our packet, or quite similar to it. It's more or less the same thing, but one of the Cl is replaced by a hydrogen. So because of that, um, because of that, you see that these all have, whoops, I'm pretty sure it's outwards. It can be wrong. I'm going to check quickly. Carbon, yeah, it's outwards. So yeah, the polarity bonds are outwards. They are polar, but this one right here, this is one of the examples we talked about. It's a nonpolar bond, and it's just one thing I remember. Like eight hydrocarbon bonds are nonpolars. It's a nonpolar bond. So in this case, there are more than one polar bonds, but not all the bonds are the same. Therefore, it may be polar, and in this case, it is because there are no lone pairs, and none of the lone pairs affect the structure, the shape of the standard geometry, molecular geometry, and in this case, it is polar. Okay, I know I'm going a little fast. Running out of time. I have to like send it to you guys before it's like 12 at least. So yeah. Next thing. I think this should be really helpful. I hope so, at least. Um, this is what I was confused about when I started the third packet, which was the polarity packet and polar bonds and everything. The last page last page of that packet. The package name is bond polarity, molecular polarity, and intermolecular forces. And the last page talked about intermolecular forces. And I'm pretty sure this is not going to be on the quiz tomorrow. I mean, it wasn't part of the syllabus, so I'm guessing it won't be. But I mean, this knowledge won't hurt. You'll go over it pretty quickly. Okay, so this is kind of a redundant question, but I just wrote it down anyway. So when I say is this, so you start off, okay, wait, back up. Intermolecular forces, otherwise known as IMFs. This is something we all learned in 8th grade, but it's like a quick thing we learned. Intermolecular forces are just the interactions of molecules between within each other. Like it's the interaction between molecules. What we learned 2 months ago was intramolecular forces. So emphasis on inter and intra. Inter is between molecules. Intra is within molecules, otherwise known as the bonds. And that's why back then we had also we also had the parameters for ionic bonds or electrostatic bonds. What are we going to call them? So yeah, we're not talking about that. That's what I was confused about when I first started the last page. It's very simple to identify how identify the IMF of a molecule. So it's a molecule polar. So this is what we did before. We determined the polarity of the molecule. Or another question you can ask is, does it have attractive forces? So if it's no, it's nonpolar. And nonpolar means it has London dispersion forces. London dispersion forces. I don't know. I don't think we talked about this in class. We talked about van der Waals last time. That was during the intermolecular forces topic lesson we learned. So these are like the van der Waals are really weak and are temporary. So this is like almost exactly like the van der Waals. This is it's like because they're nonpolar, they don't have definite partial charges, and because of that, it can be spontaneous. So if you take like because we know because we know that the electron cloud has an ever running electrons, they always move around. So if you take like a snapshot, like a freeze a time frame in space and time, this probably sometimes going to be a higher density of electrons on one side of the electron cloud, and that will cause it to have a kind of like a charge, but only temporarily, and that's why it's very weak. And and it is important to remember it is the only force. I don't know why does that keep happening. It is the only force for nonpolar molecules. So if it's nonpolar, it is London dispersion. It can't be anything else. I mean, and this is again to reiterate the interaction between molecules. So between one molecule and another molecule, so between one nonpolar molecule and another nonpolar molecule, more or less, usually the same one, same type of substance or compound. So now, if the molecule is polar or has attractive forces or overall attractive forces, then obviously it's a polar molecule. But if now you have to ask yourself if that polar molecule contains bonds between hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. And if it does, let's talk about if it when it doesn't first. If it doesn't, it's dipole-dipole. Forces. That's the right F. Okay. These are fairly strong. They have definite, important, and highlight, I guess, definite partial charges. And I guess they're stronger, and yeah, that's pretty much it. They have definite partial charges. Like it's there. There's one end of the molecule will have a partial. This is denoted as delta, partial positive charge, and a partial negative charge. And usually, the more electronegative element has a partial negative charge. And this is also how you determine the formal charges. I hope you know that. I really don't have time to talk about that, but okay. While calculating formal charges and resonance structures, the more electronegative element should have the negative charge. That's basically the same concept right here. Okay. Now we'll get into examples. I think I'll just give a couple examples. This is nonpolar CO2. We already talked about that. This, for example, right here. I don't know. Yeah, this right here, for example, we can have HCN is another example of, it's an example of dipole-dipole. Although now you will have some confusion here, we'll clear it up, but that's one example. Now, if the molecule does have these, has hydrogen bonds with hydrogen bonded with nitrogen or oxygen or fluorine, this is what we call hydrogen bond, and it's quite famous because it has a hydrogen. Or let's be more specific. It's hydrogen bonding forces. Now, the name itself is slightly, I guess, misleading because, like I said in the beginning, this is why I kept saying it. They're not actual bonds. They're just interactions. They're interaction between molecules. So this right here is an interaction. It's the name of an interaction. The reason we call it hydrogen bonds is to distinguish it from the dipole, and that's because hydrogen bond is more or less just a stronger dipole-dipole. I'm gonna write that DD. It is the strongest IMF. And obviously, it's found within hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen. So this is because it has like it can these are for it can bond with other elements or atoms. This is a happy pair, happy guy. Oh my god. It's late, guys. It's just I'm tired. I'm tired. Um and yeah, so this you can connect with other stuff and stuff. So these molecules will have hydrogen bond interaction, hydrogen bonding forces, because hydrogen is specifically bonded to one of these three most electronegative elements. Here, in this example right here, HCN, although N and H is present, they're not bonded. It's H is bonded to C, or hydrogen is bonded to carbon, which is bonded to nitrogen. And I'm pretty sure this has like two, I don't know. So this, therefore, is not a hydrogen bond. It's only a dipole-dipole. But pretty sure don't need to know this, so you could probably skip it. I'm probably should have said that in the beginning, but oh well. Okay, next thing. We're good here. Just don't worry about this. I'm pretty sure it's not gonna be on the quiz, but if it is, you can watch it and just rewatch it. It's just 10 minutes, I think. It's kind of a long video by now, but this last thing, just practice problems, and we'll be good. Okay, quick practice stuff. This is we already was done in the packet. I'm gonna redo it, and we'll be good to go. SO2. This is in our third packet with the polarity stuff. So you use your first Lewis dot structure rules to figure out everything. I already know this. To speed stuff up, I'm quickly going to draw this. Oxygen is 1, 2, 3, 4, 5, 6. If there's a mistake, forgive me. Try to get this done. So this, first step, we drew a Lewis dot structure. What happened? Okay, there we go. We drew a Lewis dot structure. That was the first step. I now have to identify, I believe, the bonds. So in this case, they are polar. By how much? By 0.86. So this is sulfur has 3.44. I'm gonna write it up here. No. Okay, my bad. 3.44. Technical difficulties, guys. Minus 2.58. Not okay. Sorry. Sulfur has 2.58, and oxygen has 3.44, which is 0.86. So it is a polar bond. These are polar bonds. They go outwards, but because there is a lone pair which affects the shape because it is bent, thus it is affecting the shape of affecting the molecular geometry of the molecule. It is therefore polar. Okay. OF2. I will come back here. It's like almost exact same thing. Three molecules. Okay. But in this case, you pretty wait, this also has, never mind. Okay, we'll just do it. We'll just go through this, okay, as quickly as I can. So this has 1, 2, 3, 4. So this has two. So this is one of the examples. It has two lone pairs. In this case, it is bent. You see, this is where you can refer to your chart, your Vesper chart, and this will look like this with F. Pretty sure these are. I'm gonna draw this already to save time. So this is like, yeah. And because it's bent and has polar bonds, doesn't matter. I mean, if it's bent and it's not going to cancel each other out. It's asymmetrical. Same over here. Asymmetrical. It's going to be polar. Okay. And you find the polar bonds by finding the electronegative differences. So you subtract the higher one from the lower one, you find the difference. If it's greater than 0.04, it is polar. If it's less than 0.04, it is nonpolar. If it's greater than 2.0, you will know it's ionic because it's going to be metal and nonmetal. So, sorry, we're good. HCN. So I just drew this like a couple of minutes ago. Now this is kind of a funny one. This one is, I believe, 0.35 or something. Yes, 0.35 as our for our. So I mean, then you don't draw this. I'm stupid because it's 0.35. It is non-polar bond. You don't draw a polarity arrow. For this, this is a polar bond. So you draw one, and I'll show you how and why. Nitrogen is something, I don't know, it's higher than carbon, and its electronegative difference is 0.49, so it has this direction, because the direction, yeah, by the way, the direction of the polarity arrow is towards the most more electronegative element. I think I told this before, said this before, but I'm not sure. There we go, we have this. So because there's nothing counteracting it, in this case it is one polar bond, one nonpolar bond. It is, although linear, it is polar, because it's one polar bond, one nonpolar bond, asymmetrical distribution, it is polar. um, Last two, probably not going to be on the quiz, but it's a little more advanced, I guess. um, Xenon, right in the middle. um, Fluorine on the sides. Okay, so xenon we know has 8. It is a noble gas, but this is where we talk about the expanded rules thing, which I don't remember what it's called, but it's the expanded rule. So these each have 6, but if you count all the electrons up in total, it's 8 plus 7 plus 7, which is 22. 22 minus 4 is 18. Now 18 minus 6, I mean 6 and 6, which is 12, is 6. You have 6 left. So in this case, you have 3 lone pairs. You see this? 3 lone pairs. Now if you refer to your Vesper chart, you will see that the 5th row, last diagram, shows you, I'm gonna do a quick sketch. Shows you that the shape of the molecular geometry is I think this is like dashed, but I don't even care anymore. Um, is linear. This is linear according to your chart. So in this case, even though you have 3 lone pairs, you have 3 lone pairs, but because it more or less, it's linear because it cancels each other's out. That's what I understand. Because it cancels, the lone pairs cancel each other out. It is linear, and now you have that out of the way. These bonds are exactly the same. I'm pretty sure it's going outwards again. It's usually outwards, guys. It's rarely inwards, but sometimes it is. Um, it's nonpolar. It's like magic. And this is more or less the same thing. Okay, you have selenium. Well, this is easy, I guess. Okay, instead of this is okay. I'm gonna do this quickly, and maybe fit another one. So you have selenium. You have 1, 2, 1, 2, 3, 4. This is an octahedral, I believe so. You have no lone pairs. I'm gonna quickly. I don't like drawing these. This is so dumb, ridiculous, just stupid, ridiculous. I don't know why we take I just don't like chemistry anymore. It's frustrating, guys. No, what am I doing? What am I doing? Bear with me. Yeah, forgive my inexperience, I guess. Okay. No, Siri, go away. That was Siri. Okay. Uh, so yeah, you have, this is an octahedral. It is no lone pairs. It is the exact same bonds. So I mean, this is like one of the shortcuts I know, or I'm pretty sure works. Um, that is not 7, guys. That is wrong. You guys are gonna kill me with this. Um, that is not 7. That is 6 right there. Sorry. Um, it's same bond. So because they're like they're the exact same bonds. You can look at the diagram and tell they're the exact same bonds. So it's gonna be nonpolar. It's like one of the shortcuts we use. I use, and I'm pretty sure it works. So trust me on that, and you will not fail. I'm kidding. I don't know what I'm talking about, but it's gonna work because if you look at it, each of these will have the same exact ENF or electronegative difference, END, electronegative difference, and because it's no lone pairs, it's not affecting the shape. It's gonna cancel each other out. Everything is gonna cancel each other out, and it's gonna be nonpolar. Now, something similar to what we just did, the one before this, the xenon difluoride, xenon tetrafluoride. Um, is more or less the same thing. It's like this one, but it's like that one and this one combined. It's like these two combined. This one and this one combined. So let's just quickly do this. And okay, when you first draw it, you will see. I'm just gonna go right into it, and I'm not drawing the electrons, guys. Too late for that. Um, when you actually work out the whole thing, you will see that you will have 4 electrons left, and thus you have 2 lone pairs. Because you have a total of 6 electron domains, um, it falls under the 6th category, obviously. And if you look at the sixth row, the 6th category, that has 2 lone pairs, this has 2 lone pairs. I'm going to be very clear about right here. 2 lone pairs. It has 2 lone pairs, but this, okay, it's gonna be really weird, but these two, I didn't draw this very clearly. If you look, yeah, when you look at the Vesper thing, these the electron pairs are on one plane, and these are on one plane. These four, um, these four fluorines are on one plane. They're yes, it sounds weird, but if you look at the bond angles in the packet, you'll see the bond angles are 120. Wait, no, never mind. It's 90 all around, and that only makes sense if there's 2 planes intersecting each other. So I'll show you what I mean. Um, I'm gonna quickly do this. So when you have 2 planes, like you have like this, and you have like one other plane crossing each other right here. This is 2 planes. So your electron pairs are over here, and your fluorines are basically these corners. And because of that, these 2 cancel each other out, and these 4 cancel each other out. And therefore, in this case, also, because every other bond, other than the lone pairs, because the lone pairs cancel each other out, the bonds are exactly the same polarity, it's going to be nonpolar. And it's a lot to handle. I'm pretty sure, I'm 80% sure, 90% sure, these are not going to be on the quiz because it's just way too confusing. And if it is, well, now if you watch the whole video, I mean, kudos to you guys who watched 36 minutes, 38 minutes of pure torture, I guess. I'm just trying to be helpful as much as I can. I hope you guys understood this. I know, a lot to take in. It's a mess. This is everything. So yeah, I hope we all do well. Good luck to everyone, and see you guys tomorrow. Peace.